Hey everyone, and welcome to today's Explainer. I am absolutely thrilled you're here because we're about to jump headfirst into what is honestly the most bizarre, mind-bending, and yet totally successful scientific framework we've ever come up with. Yep, we're talking about quantum mechanics. If you've ever looked around your room and thought you had a pretty good handle on how the physical world works, well, get ready. We're about to pull the curtain all the way back on reality itself.
Okay, let's dive right into this. For the longest time, centuries really, we were basically taught that the universe was this giant, predictable clockwork machine, just made up of tiny, solid billiard balls bouncing around. But that brings us to the massive paradigm shift we're exploring today. At its absolute core, reality isn't solid at all. It's fluid. Down at the very deepest level, the universe is actually built entirely out of probabilities, waves, interactions, and pure information. Crazy, right?
To really wrap our heads around this, I want you to imagine shrinking. We're going to zoom way, way in, past the size of a single grain of sand. Keep going, smaller than a human cell, smaller than a microscopic bacterium, zipping right past complex molecules, plunging all the way down to a single atom. And down here, at this impossibly tiny scale, the ordinary rules of life that you and I rely on, they just completely break down. The everyday physics we know literally stops working. And that brings us perfectly to Chapter 1, Shrinking into the Unknown. Let's take a look at what exactly happened when our classical understanding of the universe just fell apart. So picture the year 1900. Physics was actually in a full-blown crisis because the old math couldn't explain something as simple as how hot objects emit energy. Enter Max Planck, a German physicist with a revolutionary fix. He proposed something completely radical for the time. He said energy doesn't just flow in a smooth, continuous stream. Instead, it comes in these tiny, uncuttable packets that he called quanta. Think about it like physical coins. No matter how much you might want to, you literally cannot hand a cashier 3.72 cents, right? The smallest coin is 1 penny. You have to use whole pennies. Well, nature works the exact same way. Energy comes in these absolute minimum chunks, and just like that, the seed of quantum mechanics was officially planted. Moving right along into Chapter 2, the birth of quantum rules.
Planck definitely cracked the door open, but it was Albert Einstein who essentially kicked it off its hinges. He realized that light actually travels as discrete packets of energy, which we now call photons. And this leads us to one of the most stunning concepts in all of science, wave-particle duality. Imagine you're standing on a beach watching these big, continuous ocean waves crashing in, and suddenly they just start behaving like distinct individual raindrops. I mean, it sounds completely impossible. But light does exactly that. Sometimes it acts like a flowing wave, and other times it acts like a distinct little particle. Both are totally true, and it depends entirely on how you observe it. And the really staggering part, this dual personality applies to solid matter just as much as it does to light.
Now, what's really interesting about this slide is the wildly bizarre concept of superposition. In our everyday world, you flip a coin and boom, you get heads or tails, one definite result. Quantum particles do not care about our everyday rules. Imagine a mystery box, and inside is a magical, endlessly spinning coin. Until you actually open that box to look, nature itself hasn't even decided the answer yet. The particle exists as heads, tails, and literally every possibility in between, all at the exact same time. It's only the physical act of measuring it that forces it to pick a lane and become one single reality.
To point out just how utterly absurd this gets, physicist Erwin Schrödinger came up with his incredibly famous, and honestly highly misunderstood, thought experiment. You've probably heard of it. First, you seal a cat in a box. Next, you add a single radioactive atom that has exactly a 50% chance of decaying. Third, if it does decay, it triggers a mechanism that releases poison. Now, according to quantum math, before you open that box, the atom is in a superposition. It is simultaneously decayed and not decayed.
Which means, step 4, the mathematics literally describes the cat as being both alive and dead at the same time. Now, Schrödinger wasn't saying there's actually a zombie cat in there. He invented this to show how totally nonsensical superposition becomes if you try to drag it up into our everyday macroscopic world.
Think of it like a massive highway of possibilities. When you drive home from work, you have to pick one road, right? Route A, B, or C. A classical object takes one single path, but a quantum particle, not so much. Mathematically, it behaves as though it's testing out every single possible route all at once. It spreads out like this wave of potential, exploring the entire landscape simultaneously, and only snaps into one definite location the exact split second we measure it. Welcome to Chapter 3, Superposition and Spooky Action. If you thought things were weird before, well, buckle up.
And this brilliantly illustrates the fundamental difference we're talking about. In our everyday life, cause strictly leads to effect. It's predictable. It's deterministic. If I hold up an apple and let go, I know exactly where it's going to fall. But in quantum mechanics, cause only leads to probability. Physicists literally cannot predict exactly what a single particle is going to do. We can only predict the likelihoods of certain things happening, not definite certainties. The universe, at its basement level, is completely run by chance.
And this built-in fuzziness leads us straight to Heisenberg's famous uncertainty principle. This is the rule stating that certain pairs of properties, say a particle's exact location and its exact momentum, simply cannot be known perfectly at the exact same time. The more accurately you pinpoint where a particle is, the less you can possibly know about where it's heading. And I really want to emphasize this. It is not because our microscopes aren't good enough. Nature itself literally enforces these strict speed limits on information. The universe fundamentally refuses to let you know everything at once. Let's anchor the uncertainty principle with an analogy that's a bit more relatable. The hummingbird in the dark. Imagine you're trying to take a photo of this super hyperactive hummingbird in pitch black darkness. The only way you can possibly see it is to turn on a flashlight. But the very second you hit that bird with the beam of light, you startle it. The light itself inherently disturbs the bird. It's the same thing at the atomic scale. The mere act of measuring a microscopic system inevitably alters it. You absolutely cannot observe the quantum world without changing the reality of what you're looking at.
Which brings us to what might be the absolute wildest concept of the whole bunch: entanglement. Einstein famously referred to this as spooky action at a distance, and he really didn't like it. Imagine two perfectly synchronized dancers. They're practicing so perfectly that even if you separate them by millions of miles, put one on Earth, one on Mars, their movements stay mysteriously linked. When particles become entangled, measuring one of them instantly determines the state of its partner, zero delay no matter how far apart they are. I know it sounds like straight-up magic, but today, entanglement is one of the most rigorously proven phenomena in all of physics.
Let's move to Chapter 4, Powering the Modern World, and see how this builds into everything around us.
You know, it's so easy to sit here and think all this quantum weirdness is just abstract chalkboard math. But let's zoom back out for a second. Smartphones? The billions of tiny transistors inside them only work because we know how to manipulate quantum behavior. Modern computers, the entire internet, totally reliant on quantum material properties. The lasers scanning your groceries, MRI machines saving lives by using the quantum spin of atomic nuclei, even the GPS in your car relies on quantum atomic clocks in space so you don't miss your exit. Quantum mechanics isn't just some fringe theory, it is literally the invisible engine powering modern civilization. Which brings us nicely to our final chapter, reality as a symphony.
Realizing that these invisible, super bizarre rules are constantly shaping everything requires a massive shift in how we see the world. Under classical physics, we saw reality as this cold, precise, deterministic machine, just gears taking away. But quantum mechanics gives us this breathtakingly dynamic picture. The universe isn't a rigid clock, it's a fluid landscape of information. It's literally a symphony of possibilities, all built from waves and probabilities interacting together to create the solid stuff that you and I actually touch and feel.
And naturally, digging into all this brings up some huge questions. The big one we hear a lot: is quantum mechanics just a theory? Honestly, this comes from a major misunderstanding of the word. In science, a theory isn't just some random guess you make over coffee. A scientific theory is a rigorously tested, battle-hardened framework backed up by mountains of real-world evidence. And the truth is, quantum mechanics is actually one of the most successful, incredibly accurate theories in human history.
Here's question number 2, and it's a fun one. Does human consciousness create reality? Sci-fi movies and late-night philosophy absolutely love this idea. But if we stick to the physics, the firm answer is no. A measurement in quantum mechanics does not need a conscious human brain looking at it. Any physical interaction at all, even just a stray particle bumping into an atom, is enough to collapse that wave of probability into one definite reality. The universe really doesn't need our minds to force it to make a choice.
So the crucial point is, if everything is quantum, why don't we see this weirdness on a daily basis? Like, if I throw a baseball, it doesn't just spontaneously blur into a wave of probability. Well, the answer is that constant, relentless interactions with the environment force large objects to act classically. All those weird quantum effects get scrambled up and basically washed out by the time you reach our everyday size. The weirdness is still totally there. It's just buried incredibly deep beneath the surface.
And that brings us perfectly to our ultimate takeaway for today. Quantum mechanics is simply the science of how nature behaves at the absolute smallest scales, a place where comfortable certainty melts away into an astonishing world of pure probability. So I just want to leave you with this final kind of mind-blowing thought. The next time you pick up your phone or just feel the warmth of sunlight on your face, remember that underneath that perfectly normal surface is a hidden, vibrant symphony of endless possibilities making the whole thing work. You are literally holding a piece of quantum magic in your hand right now.